Okay, excellent. So welcome everyone to the second episode in the Quantum Server Open Webinar series on scientific computing applications. I already provided a general overview of our company in the first webinar, which happened last Tuesday. So I'm not going to repeat everything. If you want, you can replay that webinar on YouTube. So I think this time it would be better if we just go straight to the presentation. So today we have the pleasure of having Professor Prafulla Jha from the University of Baroda in India as our guest speaker. And today, so he will be presenting on computations for materials design at reduced dimension to extreme conditions. Okay, so Professor Jha, over to you. You are ready to present, and I will just make you host in order to start your presentation.
Okay, thank you, Gabriele. Thank you very much.
Yeah. Okay. So now you should be ready to be hosted.
I can share now screen.
And you should be able to share your screen, yeah.
Okay, I hope my screen is...
yeah, we can see it, yeah.
You can see, right? So,
yeah.
Go into the presentation mode, right?
Yeah, sure.
Right? So, yes, formally I will thank Gabriele for giving me this opportunity for presenting something related to my work. See, I am sitting here, so it is because you all are online. So let us see that where I am sitting in India at in this state, which is enlarged here, and this is the city where I am sitting right now. Right. So, as you know, that my topic of presentation is computation for materials design and reduced at reduced dimension to extreme condition. This is basically, I choose a topic by considering that we do the computation for material science and in the variety of area or at the for the variety of problem, and that you can see that we actively work in the field of nanostructure, nanomaterials, apart from the usual bulk systems. And then the materials at extreme conditions. Extreme conditions, I mean here that you can have the stress, you can have the pressure, you can have many other variables, right? So even, so this is what I have put briefly. Of course, it will be not possible to go into the detail for everything, or maybe even for a few topics in detail. For that, what I have done, just I am briefly mentioning here that what are the areas in which we are working, that is mainly. So as you can see that one area that we work is in the bioconjugated nanostructure materials, and we use here several two-dimensional materials for bioconjugation, and those materials are then basically used, or those combination or systems are basically used right from the detection or the absorption, sensor application to the neurotransmitters and all other things. Another, as I said, that materials at extreme conditions and geophysical implications. I don't know whether I will be able to cover geophysical implications or not, but the point or the matter is that we do the DFT simulation or DFT calculations for the materials, and even with some experimental part, because I have a Raman spectrometer. So using that, we do the materials characterization at different pressure, and then we normally use it for some materials because we have some collaboration with the earth science departments. I have also one project also, so we try to put it in terms of their geophysical implication. But the point is that mainly here I will be showing that under pressure or under stress or under strain, how the materials basically show the different characteristics. Mainly I will focus here the structural phase transition in one of the systems. Then another area in which we work, that is the thermoelectric materials. That is materials we design, we design several materials from the thermoelectric point of view. Basically, the motive is to have the large enhancement. And here I will, in the last, basically, I will be focusing on the phonon parts, because that's a very important parameter in the thermoelectric figure of merit. And therefore, how the thermal conductivity plays the important role, and some aspect of the negative phonons or something like that. Then we also work in photovoltaic properties of the materials. Here I will be talking about the very famous hybrid organic inorganic perovskite, that is MAPI, what it is known as, and in the two-dimensional as well in the bulk, but here it is focusing on the two. Then we work in the catalysis. Then we work for the nanostructures, mainly here we consider that the core cell type of nano wire, or the heterostructures, for again for the several application point of view. Then you can see here that one topic normally is slightly away from this, that is a drug design and drug delivery system. So here we basically do by using the density functional theory calculations and the molecular dynamic simulation, we basically design some molecules for the drug application. And apart from that, by using some nanostructures, that is, there are a few papers which we have recently published related to the drug delivery systems. And then, of course, graphene and the graphene-based composites are there, because that is where everything starts as far as the two-dimensional systems are concerned. Right? Just in beginning, I am putting this because all the studies here that will be reported is based on the density functional theory. I will not go into the detail because everybody is from this field. Right? As I said, that our focus will be particularly only in one area, and today I have selected that is for the energy application, and that too, even the phase transition or the structural phase transition or the extreme condition I will be talking, that will be also related to the in energy applications only, right? Because this is something which is a very important topic nowadays, and covers a lot of area from the application point of view, whether it's a photovoltaic, whether it's a thermoelectricity, whether it's a catalyticity, or several other things, right? So I will focus on energy related study, that is application of 2D materials, you can say, for the energy application point of view, because that is what, as I said, it's a very important aspect nowadays. Like what we know, that our civilization, modern life, you can say, that depends on the energy, right? Whatever we see, that is whatever we develop or whatever is being developed, that is devices, electronics for applications in medical, military, or in the, whether it's a societal or the civilian application, that energy is a very important parameters. And you can see here, therefore the energy is in high demand, right? And this particular graph you can see, if we, that means basically we can have, in another way we can say that our energy is sufficient only for the 10 billion people, right? So what it is, if suppose we assume that the 10 billion people exist and they consume the 3 kilowatt energy or per person, then you can see that there is a large gap between the world power demand and the availability of energy, particularly from the fossil sources, like fossil, hydro, non-breeding, fission, and all of that. That means this gap is there, and one needs to sorry, fulfill it, right? And we can see that most of the energy supplies at present is from the fossil fuels, and that can be seen in this pie graph. And because the most of the energy is at present or is basically from the fossil fuels, therefore there will be a quite high rise in the costing, and that you can see the bottom or account that Howard predicted that the global oil production would peak around the year 2000 and trigger an energy crisis with power blackouts and rising cost of the energy and fuel. That means basically that once we will approach towards the end of the fossil fuels, naturally the cost will rise because the demand will be more and the availability will be the less. But the problem with the fossil fuel is that even if you use it, it's pollution because they are the source of the pollution. So you can see here that air pollution from the coal burning industry, that is one thing. Then how these pollutions basically affect us, or how these issues such as cost rising, etc., affect us. That suppose there is a petrol prices hike, and that is anyway it is Indian example, which is record high liter of petrol in Delhi. Then you have the pollution in Indian capital Delhi. Then you have the health and that will health and quality of the life will be disrupted, right? And because you will not have the petrol, naturally people will walk on foot, and those kind of problem will be there, and that those things basically will lead to the economy in terms of because of the mass migration and the security threats, right? So these are the basically required. These are the basic problems associated with the fossil fuels or the fuels which are available right now. In this graph, you can see here that you have the coal, you have the natural gas, petroleum, renewable energies, etc. And therefore, we can say that the solution of this problem is basically what is in terms of the renewable energy. That means you should have the renewable energy, and these are the examples that we can assume that hydroelectricity, then several uh, non-renewable sources. These are all renewable sources. So non-renewable sources is the energy sources is the only thing that is basically required. And those things will come from where? They will come basically from the solar energy and one from the hydrogen. So solar energy and water is considered as the renewable energy sources. And you can see from this that in 1954 the efficiency was 6% and could produce only the 20 watts, while in the 2020 efficiency is around 20% and it produces 320 watts or so, right? And another is the hydrogen source. The hydrogen is considered as cleanest and the green form of energy. So these two cartoons, one related to the photovoltaic effect, or another is that is the hydrogen source, both require the materials. That means we have to develop the materials for both both applications, that is whether it's a photovoltaic application or the hydrogen related application, with hydrogen storage, maybe the. So these, for both of these, you require the novel materials which can produce energy, right? So materials to save ourselves. So these are the some of the things, materials engineering, when you can see that high temperature superconductivity, by making artificial intelligence, we can develop the material. That is what we need. We have done these things, right? Superconductivity, we have the materials, we have now some idea about the, or people are using artificial intelligence or the machine learning, but still much are to be done, right? And therefore, because everything finally ends on the materials, and let us see that what are the materials in our life. So we have in terms of material, we have in our life as bulk material. Then we have the two-dimensional materials, one-dimensional material, and a zero-dimensional material. That means anything you can see from our eye, or you can see from our eye, are the bulk materials. Then you have the two-dimensional material, and very popular now after the discovery or having the graphene. Then because of this graphene, you all can know that the two-dimensional materials have been revolutionized, or every day you'll find some or other two-dimensional materials to predict, mostly by the density functional theory calculation with the help of machine learning or artificial intelligence. Then you have the one-dimensional material, right? That is carbon nanotube. Anyway, it is known because it came before the graphene, in fact, you can say. Then you have the nanoparticle or the quantum. So these are the different class of materials which you can have, and they all have the different properties. I am not going into the detail of these things, but these are the possible materials which can be used for form of the material which can be used for the energy application which I have shown earlier, right? Now let us see that. What are the requirement advanced material technologies that can save the environment are technology based, and that will be that for that you require the device and material, and what are the applications. So if you want to control or and the monitor, then you require the sensor and actuators, right? And that will be used for the environment pollution monitoring, satellite ozone layer observing, or in the brief we can say we can use it for the pollution control, right? So we have to develop the material which is for the technology that is monitoring and control based. Then you have the saving energy. So of course we all know superconductors, let us consider, that can be used energy storage, power cables, then generator, communication device, and the system. Then you have the new energies. So in the new energies, as I mentioned in the previous slide, that we have the photovoltaic cells, we have the solar cells, we have photocatalysts, and the hydrogen storage. They will be used where? For the dry and wet solar battery, electricity production, hydrogen production from water, and the hydrogen energy sources. So we have monitoring and control, saving energy, new energy, and the last one is the environment related technology. So of course that will be photocatalyst, ceramic membrane, and the environmental catalyst. And they will be used for decomposition or the purification of the polluted water, gas separation, purification of the polluted water, reduction of environmental pollutants like nitrogen oxide, sulfur oxide, catalytic combustion, reuse, recycle of the carbon dioxide. So that means for everything which is related to the environment, let us consider, require a new or the new kind of material. And since this is material, and therefore we always have the possibility to improve, right? In a very simple word, if I say we have 10 to the power 23 atoms, and we all are mostly the DFT persons or the first principle calculation person, even a single atom position changes the property. So we have a lot of opportunity to have or to produce the new materials for the better societal application, whether environment or the energy, right? So if we want to develop a new materials, what should be the properties of that? It should have the tunable properties, highly abundant and easily available, sustainable and renewable. It should have low cost. It can be synthesized in large quantity. It should be non-toxic and separable, lightweighted, and those are what, in terms of properties, you can say tunable band gap, higher peak conductivity. I will discuss this in terms of solar cell somewhere. Higher optical transparency, gives free energy vicinity of zero, dynamical stability in bulk and their respective nanostructure, enhanced mechanical properties, greater central and sensor sensing as ability. That means if we design a material, or if you want to plan to design a material, we must keep these parameters or these things in our mind, that we, particularly in context of energy, that we need to see that. So therefore the categories of material, right? And as I said that after coming or after discovery of the graphene, lots of two-dimensional materials have been proposed, predicted, and being predicted every day. People try with the different combination, and finally they do their study starting from the electronic band structure to some application. So let us consider what are those materials can be categorized. It's a chalcogenides, phosphites, nitrites, sulfides, and oxides. And these are the examples, right? That we have the lot of chalcogenides, lot of people work, including us. Phosphite, many people work. This is another class of material. We have worked on the boron nitride also. People work on this. Then you have the sulfide. We have the oxides, right? So here, basically, I have considered two oxide system. One is the Delafossite, and another is the perovskite, and then one chalcogenides from this group for the energy applications, as well as suitable, as well as for the phase transition and all that, right? So therefore, now my focus only remains in the third point, that means for the energy thing. And I said that I have gone for the photocatalyst, solar cell, and the hydrogen energy. So let us start with the photocatalyst. This is the sum of our publication which falls in this area, and I have put here. Not I will be covering all, right? Even after that, we have several papers. I'm not going to cover them, but I will be selecting one or two from this, and then I will be discussing. So let us start with the Delafossite. I have chosen this because of two reasons. One, that it covers my energy aspect, right? It covers my reduced dimension aspect, as well as it covers also my approach for the extreme condition. That means by applying the pressure, how the material's characteristic change. So let us just come to this particular material, very known material, and very recently it has been shown that this material can also be used for the hydrogen production application, or rather you can say the energy application point of view, right? So these are the popular materials in this category, and this is a main mineral was named on in honor of crystallographer Gabriel Delafossite, and Delafossite materials are well known for their high optical transparency and p-type conductivity and better hole mobility, right, without any intentional doping. And the combination of these two makes this material very suitable for the transparent category of the transparent conducting oxides. Therefore, the Delafossites have been proposed to be useful in many areas, including in the solar energy industry. However, they have some drawbacks, and that is why we are trying to reduce the dimension. We are trying to have the extreme condition so that the drawbacks of these materials can be minimized. For the application of TCO, that is transparent conducting oxide, the currently available TCO such as zinc oxide, tin oxide are mostly N-type. Hence, their use in device applications is limited due to the lacking of good P-type semiconductor. Right? So these are all N-type material, and they have the limitation. So drawback in bulk Delafossite, that is general view, wide band gap, low surface area, or the low reflective reactive surface. Localization of holes near oxygen atom, it has low p-type conductivity, large hole effective mass, and this is what are some indicative graph, that is how effective mass for the electrons as well as the holes in selected binary and ternary oxide you can see from here. So for the electrons, if we see that is the number of compounds are more with the lower effective mass, and so on. This is what the localization of holes, and this basically shows that the materials possessing the hole effective mass and with the relative dp. Right, so what we thought, let us have the two-dimensional Delafossite, right? So normally when you have the layered structure, it is easy to make the two-dimensional structure. So since you can see this is a two-dimensional material, so we can cut one layer from here, right? In fact, in one of the slide, I will be showing that we calculate the expression energy, right? And based on that also, we can decide that whether it is easy to remove or it is difficult to remove, right? So a 2D material is all surface, and so that means, as I said, that surface is more, and that is why they are useful. The 2D nano might be an effective strategy to improve the electronic properties of Delafossites and to bring about good photocatalytic and good photovoltaic abilities. And this is what our assumptions, right? So as I said, that you can cut like this, and sorry, this will be the two-dimensional. So now let us, we have the two-dimensional material, and we have now, we can make the monolayer of one of the Delafossite type of compound, the COOH, towards hydrogen evolution reaction and the OER, right? Uh, See, the phonon dispersion calculation nowadays is very important. It has been always important because it it is related to several properties of the material, right? But nowadays, when we talk about a two-dimensional material, it is very important to check the stability, right? And therefore, if you do the phonon calculation, and if your all frequency of all phonon branches in the entire beryllium zone is real, we say that okay, the materials will be the stable one, and therefore we calculate it. So a two-dimensional material, uh, we have we made it for the cobalt ox- oxide COOH, and you can see here that you have the phonon dispersion curve, and it shows all phonon branches are real. I will be talking more about this in the last um, uh, real, and therefore they are stable. Right? This is the band structure of this same compound in the two dimension. This work has been published in another journal, right? Right. So what we did, effect of, so we basically wanted to have the hydrogen adsorption and the oxygen adsorption for the hydrogen evolution reaction and the oxygen evolution reaction. And then this is what basically that we substituted here the hydrogen and the oxygen. Of course, it has been done for different sites and other thing optimization, right? And you can see the changes, right? And this is what is the bond length profile of in plane oxygen atom. And in this, basically say that hydrogen absorb two-dimensional COOH, and oxygen absorb two dimensions in comparison with pristine and pristine 2D COOH. White, red, and blue squares represent the OO, OOH, OO bond distance respectively. And what basically we see that that there is some kind of a disruption, right? That means this is when this particular is because of the hydrogen absorption and oxygen absorption. Here it is hydrogen, here it is oxygen, and therefore you can see that some kind of destruction is observed, but that is what is the proof that it has been absorbed, right? So it is basically the density of states. So density of states in this case you can see that has been plotted for hydrogen adsorb, as well as it is the charge density plot. And we, as I have shown in the bond previous cases, that the bond length profile of 2DCOH shows that the add atom, that is hydrogen and oxygen, induces distortions around its own surrounding. And in this case, basically you can see that the change in the density of states, A, that is upper one for the pristine, and the lower ones are the this. Here the lattice parameter is slightly modified, and this is the energy energy at X point. Whole theory basically lies for the electrostatic electrocatalytic approach for hydrogen and oxygen revolution reactions over preferably sites are. This is what is the basic reaction, right? Where H star O star signifies hydrogen and oxygen adsorb on the surface, where E adsorption is the adsorption energy of hydrogen and delta E represents the 0 point energy difference of hydrogen molecule or oxygen molecule in the adsorbed state and the gas phase. And therefore, E adsorption at this particular thing can be expressed by this expression, delta SS, that is entropy term is like that. And because of the fact that vibrational entropy is small in the adsorbed state, here S0, this term is the entropy of H2 in the gas phase having 0.4 electron volt value at the standard experimental condition. So that means basically if after substituting the Gibbs free energy for the hydrogen adsorption should be E adsorption plus 0.24, and if any system which has the delta GH star closer to the 0 is considered to be the good, right? So here where 0.24 EV is the contribution from ZPE and entropy at 298, and therefore you can see that if E adsorption comes closer to 0.024 minus, then it is very good. Similarly for this. So in this particular compound, or COOH, delta GH star and delta GO star, the free energy of hydrogen and oxygen is given here. So E adsorption is here minus 0.45 electron volt. Delta GH is minus 0.21 electron volt, while in the oxygen we have there, right? So you can see that this particular thing for the hydrogen adsorption, it is very good. Right? This is what briefly, if I go for those things, the geometrical optimization of pristine hydrogen and oxygen adsorbed two-dimensional COOH depicts that the hydrogen and oxygen atoms prefer top side of oxygen atom of two dimensions. So because as I said that we have optimized with different configuration, it is related to bond length. On adsorption of hydrogen, additional electronic energy states are induced at the Fermi level, turning two-dimensional COH to a metallic, whereas an oxygen band gap reduces significantly by 82%. The calculated Gibbs free energy of hydrogen and oxygen adsorption indicates that the 2D COH is better suitable for HER than the oxygen evolution reaction, that is the OER. That is what I said in the previous slide. So we can basically see that the 2D COOH is a very good material for two-dimensional, so for the hydrogen evolution reaction. Now let us come to the solar cell part, solar cell 1. So here I have selected a very popular material, perovskite material for the for this study. So what we have imposed here, that we have imposed a strain and we change the number of layers and study the electronic and optical property, and then try to see its implication for solar cell application, right? So without going into the detail of this perovskite and all the things, we know that these are perovskite material, particularly this one, this MAPI, CHNH3, PB, I3, PB, CL3, PB, BR3. It's very important because very high efficiency is observed in this within the discovery, within a very small time or a small period of its discovery. It has high absorption coefficient, high diffusion length, high charge carrier mobility, and a very high values of open circuit voltage, right? But it has the major drawback in terms of its stability or degradation, right? So CH3, NH3, PBI3, that normally called as the MAPI, MAPI is that CH3NH3 is methyl ammonium. So methyl ammonium lead iodide degrades in humid condition and form TbI2 at higher temperatures due to the loss of CH3NH3 ion. Lead is a toxic compound, right? And therefore it is harmful for the intron. So the two major drawback with this organic inorganic hybrid perovskite is that they are not stable and they are toxic as long as PB is good. But people are trying with different, as I said, that PBI, VR, etc., etc. Right? So what we again thought to have the low dimensional counterpart of this, that is two-dimensional and the one-dimensional structure. Because I assume that everybody knows the DFT calculation over here, so I'm not going into those details of the parameters. Just only I'm trying to focus on the results what we got it. So in the case of three-dimensional material, we have the 1.675, and anyway, these are all published works, so I have I'm mentioning that also. So if anybody has want to know in the detail, you can follow the paper. When it is a two-dimensional material, the band gap increases. When it is a one-dimensional material, the band gap further increases. So after that means basically what the confinement or reducing the dimension increases its band gap. That is one thing. As far as the band gap part is concerned, we have one thing that band gap increases from going from 3D to 1D, and that is basically due to the quantum confinement, right? So this is what is the density of states calculated for all three forms. So you can see in 1D the band gap is 2.40, while in the 42, while in the case of MAPI, 3D, it is 1.675, right? And these are the parameters for band gap, effective mass, whole effective mass for bulk 2D and 1D, right? So you can see that in 1D we do not have any experimental thing, but 2D we have some reference for the band gap comparison. So what we say that ratio of DOS at valence band edge and the conduction band is highest in 1D mapping, which indicates greater relaxation rate for holes than electrons, right? Quite obvious. The lower effective mass of electrons and holes, which arise from a strong sp anti-bonding coupling, is quite useful for PIN configuration of the solar cell. This suggests that the 2D MAPI is better for thin film solar cell because of its use in PIN configuration, right? So this is what is the optical properties we have calculated for all 2D, 1D and the 0D. So absorption coefficient plays vital role in the fabrication of solar cells. We all know it attains minima around 4.6 to 5.0 electron volts, suggesting that MAPI, that is CS3, NS3, PBI3, to be transparent for high energy incident photon and exhibit metallic nature in this region. Then absorption spectra shows a blue shift confirming an increase in the band gap of 1D MAPI. So this is absorption spectra. We have calculated and then increase the band gap of 1D MAPI as compared to its bulk and 2D counterpart. And then we have also calculated, which is an important parameter for calculating the solar cell parameters such as efficiency, fill factor, or voltage, open circuit voltage, and all of that. So joint density of state have also been calculated for all this. I will analyze this later, right? So calculated, therefore, by using the band gap, then by joint all these parameters, we have calculated the solar cell parameter, and basically we have tried to see the implication of this material to the solar cell application. So this is the schematic of solar cell device fabrication. You can see glass, ITO, then it is MAPI, PCBM, HTM. So these basically are changed. Sometimes you take the two materials are there, PCBM and then the TiO2. So we have shown with both, right? And then on the top you have the silver, and then basically the sun, right? So you can see here that in the case of TiO2, right, that means here it is red one. TiO2, you have the VOC for the bulk as 1.14, for the two-dimensional it is 2.15, while it is for the 1D 1.75. This is the GeSe, it's a very important parameter for the solar cell efficiency. This is the kill factor, and this is what is basically the efficiency, right? So you can see here that efficiency is quite high in the case of 2D. There is not much difference you can see basically in calculated one in the bulk and the 2D, right? But it is certainly much more higher than the one-dimensional case, right? Similarly, it is true for both, right? So both configuration, we get the same thing. That means, but basically I wanted to convey that by reducing the dimension from bulk to 2D, in the case of MAPI, and in fact this is, and there is an experimental evidence for this also, that it shows the efficiency is highest in the case of two-dimensional counterpart of this mapping. And since now it is the two-dimension, that means one layer, and therefore we thought to have the application of a strain, right? And another application, that is by increasing the numbers of the layers. So whether with number it reduces or increases. But anyway, as you can see from here, if you are increasing the number, that means approaching towards bulk, and therefore it will reduce the, reduce the efficiency, right? So this was for the maximum, right? Therefore now we have the, as I said, that telling electronic properties of 2D MAPI, that means basically the strain dependent and the layer dependent, the strain dependent, and you can see here that that with strain how the efficiency basically increases. So for the 2%, you can see this is what is the maximum. Strain you can also assume in a such a way that, okay, let us, you have the surface or a substrate, and you are growing your film on that particular thing, right? So in both conditions, the 2D MAPI shows a progressive opening of band gap upon increasing tensile strain is observed, and band nature at turns indirect to nature, right? So I will go slightly faster now because I have to cover one more thing. The maximum efficiency of 23.6% is observed in case of 2D MAPI, right? This one, right? Thermoelectric material, which is another very important class of material, the class of energy application. This is what is shown. The materials are receiving wide attention due to their potential role in mitigating global greenhouse effect and enable conversion of waste heat energy directly to electrical energy, right? This is the same graph which I discussed in the beginning, but you can see here that how total energy consumption is increasing. That is the same thing which I presented here. This works on the basis of that you have the material, one region is hot, another is cold, and that produces basically the electricity. So the applied temperature difference in the material stimulates charge carriers, whether it's electron or to spread from hot region to the cold region, causing flow of current over the circuit, right? So this is number of publication related to thermoelectricity, so I will not go into this. Let us come to this point. This is the important slide as far as the thermoelectricity is concerned. The efficiency of the thermoelectric material is considered is decided based on a parameter called figure of May. And everybody's aim, or even our aim, or everybody's aim is basically to maximize this density, and that is given by this expression. This is a complicated expression in the sense that one thing that is, this is electrical part, let us, or electronic part, let us consider. If this increases, this decreases, and then they have a very complex relation, right? And therefore, to control or to have the large Gete is a very difficult task, right? So this here you can see in a very simple manner that this is K, which consists the electronic thermal conductivity and the lattice thermal conductivity. So if you reduce this K, your job is done. As far as this K is concerned, this is electronic and the numerator is also the electronic part, and therefore if this increases, that will also increase, doesn't affect significantly. But this is what is the KL, that is a lattice thermal conductivity. So now the whole aim of the present studies are basically focusing on the reducing the lattice thermal conductivity, right? That is because of the phonon. And that can be done by using one method. So whether you may change the structure, that means by nano structuring the material, you can modify the thermal conductivity, or otherwise you can just change or tune the phonon behavior or the phonon dispersion. So both I will be showing, right? This is timeline, so I will not go into this. So the time is right. So this is different class of materials which show the reasonably or significantly figure of merit for some of the traditional materials, right? Here I will focus on two materials, that is the GeSe and the GeSe, very famous chalcogenides. You can say basically these are the benchmark material for the thermoelectricity, right? So you have, this is what is the parameter, this is how the structure is there. This is what I was basically saying you in the at one slide, that you have a layered structure and you can exfoliate it, and exfoliation energy you can calculate. If it is large, it's difficult to exfoliate. If it is less, it is simple, because in that graph I have shown you that by scissor you can cut and make it. So it is not basically that simple. You have to have the removal is based on the exfoliation energy, and that basically one calculates, right? So just I will, because I was talking regarding the thermal conductivity, lattice thermal conductivity, so let us see what is phonon, right? So phonon is a quantum of lattice vibration, and it helps in understanding several properties, lattice dynamical properties, stability, phase transition, IR and Raman spectra, electron phonon interaction, that means superconductivity, then the heat transfer in solids, then optical property, and many other, right? Our focus is here right now. So two types of phonon, one is acoustic, one is optical. I'm telling you because we will be seeing in last that the thermal conductivity is significantly controlled by the acoustic phonon thing. This is the phonon modes in two-dimensional materials, that one extra mode. See that in the phonon dispersion curve, you have optical phonon, you have acoustical phonon. In optical, you have longitudinal transverse. Similarly, in the acoustic, you have longitudinal acoustic. But when you have the two-dimensional material, we have additional out-of-plane acoustic vibration and out-of-plane optical modes, right? And they also played a very important role, particularly when you have any two-dimensional material, and you must have observed the rippling. So the rippling can be controlled by controlling this Gete, right? This is the methodology, how basically the phonons are calculated, right? So in the first principal calculation, this is we obtain K matrix at few wave vectors in the billion zone. Then we use the Fourier series to transform KQ to KR, that is the real space force constant matrix. And then by obtaining KQ at arbitrary wave vector Q, eigen spectrum, that is eigen DQ, that is eigen matrix, which is given by this, is solved, and the phonon modes at each or every K is calculated. As far as the experiment is concerned, you have Raman spectroscopy, that is first order, second order, Brillouin spectroscopy, neutron scattering, IR spectroscopy. Nowadays, even the people use the X-ray scattering also to know that, right? This is graphing, I will not go, just only to focus that how the phonons are useful in giving you the information, right? when graphene was discovered, naturally it was observed characterized by using the Raman spectroscopy. So two major peaks, one at 1586 and another, this is basically the double of the mode which is observed at 1300 or so. D band, this is so D band two phonon process, that is this is D band. So most prominent here, and D band can be controlled, or you can measure the shift by changing the number of layer or by chemical doping. Now when you have the phonon dispersion curve, what information basically we get? Phone anomalies occur for wave vectors Q, that means at the Dirac point, right? As in the case of electronic band structure, we have very uh, typical behavior at Dirac point, that is Horn anomalies occur for wave vectors Q that connect 2 points, right? That means basically here, right? So think in the highest optical branch at gamma and K, right? And slope around gamma and K proportional to electron phonon coupling. So if you find the slope, we can have the idea of electron phonon interaction. So basically point is what? That you have the phonon dispersion curve, you can get several information related to what we require in the two dimension. This is what is our study. Just only I will focus one thing. These are performed with two different study. Only thing you can see here that as this is 4 layer, right? So we have done single, bi, dry, and 4 layers. If you have the 4 layer, that means this is out of plane acoustic mode. Out of plane acoustic mode is splits right in the bottom. And if you go for the large number of layers approaching towards the graphite, then you will find that this frequency somewhere approaches around 90 or 100 or so. That means from here also you can approach that. This is for the graphene oxide. Our motive was what? To design the graphene oxide model to see the ratio of oxygen and the carbon and how its electronic property changes. But before having the electronic property, we must have the stability of the material. And this is all you can see the phonon dispersion curve. All phonon modes are real, therefore they can exist. And this one is the different models. So different models means different concentration of oxygen and the ratio of the oxygen and the carbon, or maybe some structural changes. And we observe that the band gap can be tuned from 0.8 to 4.0 electron volt. Similarly, by changing the oxygen carbon ratio, again you can change the band gap. So oxygen carbon ratio is another parameter which tunes the band gap in the graphene, right? Right, so this is another material that is very famous as far as the two-dimensional material is concerned. So this is allotropes of boron nitride. We have worked in all boron nitride structure or the phases, cubic, bulk, hexagonal, nanotube, halide, the new one. Then the graphene dioxide, we have the boron dioxide kind of structure that we have depicted. So I will slightly rush through. This is what is the strain dependent phonon dispersion curve, and that basically is done with several strains, and at particular strain you can see that here the phonon here, right? So phonon branches become negative, right, or imaginary, and therefore this structure is unstable. But up to 15% of 12% of strain, the boron nitride sheets are possible, right? So it can sustain. So for how the phonon dispersion curves are different, right? Basically what, how the out of plane mode comes, the out of plane modes results because of the layered structure, right? So in the hexagonal boron nitride, we have the layered structure, and therefore we get the ZO and the ZA. While in the case of cubic, we don't have, and therefore we don't get any out of plane acoustic mode or optical mode, right? So this is all one. I will come to the last point so that, right. So we have calculated, let us consider for 2D hexagonal boron nitride and Heckelite boron nitride. That means the structure is different. And you can see that the lattice thermal conductivity reduces tremendously in this. That means the Heckelite boron nitride is a good material for thermoelectricity application if we do it, right? So our focus was only thermal conductivity. So we saw that the thermal conductivity reduces significantly in the case of Heckelite boron nitride, right? So this Heckelite, uh, two-dimensional. So this is all parameters. That is how the Bunsen parameter varies, how Heckelite, in the case of Heckelite or in the two-dimensional, because I wanted to show the one important thing, so I will basically like, the second part was that extreme condition, right? So GET is a very, I mean, benchmark material as far as the thermoelectricity is concerned. But in the ground state, it is rhombohedral, and go it it goes from rhombohedral to the orthorhombic or the cubic, and they have the different paths, right? So that means basically from at 3.5 GPa, it becomes FM3M, that means NaCl structure, and then at PM, that is a cube, CaCl type structure, it goes via these paths, right? One path is this, another path is this, another path is this, another path. So by applying the pressure, you can have the different phases of it. But I will only go through few things. You can see here that it is basically the rhombohedral structure, and we have calculated at normal condition, and you can see the phonon dispersion curve that all phonon modes are real, and therefore R3M or the rhombohedral phase is stable. While at the same condition, the FM3M, that is the NaCl phase, is unstable because phonon branches are imaginary. Then you have the CaCl phase at the same condition. This also shows. That means at normal condition only rhombohedral phase is considered. But now when we apply the pressure, you will see that at 3.1 GPa, that in the cubic phase or in the NaCl phase, all phonon branches turn positive, right? Here also you can see, but how basically it goes, that is what it is shown. So you can see that at 3.1 GPa, cubic phases or the NaCl phase is stable, that is where all phonon modes are positive. When it comes to the 33 GPa, I have chosen the part, this part, right? So you can see here, so all phonon branches are positive or real at 33 GPa. So at ground state, RM3M, that is rhombohedral. Then at 3.1 GPa, it is cubic phase or NaCl, NaCl phase, and then another cubic phase, that is the CaCl phase, comes at 33 GPa. So you can see that by phonon dispersion, you can know the phase or structural phase transition of the material, right? So by calculating it. Here just K lattice, that is the thermal conductivity I have to. So all three phases you can see here that this is CaCl phase, so it is very high. It is RM3, that is blue ones are the rhombohedral, and the red one is the FM3M. Of course, right, thermal conductivity at lower temperature is very high for CaCl phase, while considering the NaCl and the CaCl phase, there is some difference, but as temperature increases, you can see that the both thermal conductivity for both phases are approaching towards this. Right? I will see it is a two-dimensional structure of this. Only thing I will show in the last, leaving all these things. I have compared the K lattice, that is thermal conductivity for Gete and GeSe, that is two-dimensional Gete, GeSe. Here you have the mode-Brundtland parameter, an important parameter for deciding the thermoelectricity in the material. So higher value of Brundtland parameter leads to a strong inharmonicity of Gete, that is the blue ones, monolayer, which further makes low value of lattice thermal. That is how it is gone, right? Now I will come to another very important point. Those who are listening and want to perform the phonon calculation. In the case of two-dimensional material, many people report negative phonon or imaginary phonons, right? So here you can see the reported GET, and it has the negative phonon imaginary, but it's a very small one, right? So, but to overcome this, you have to, if it is really a stable system, then you can overcome this by doing calculation at higher with higher efficiency, or that means basically the higher threshold. And that is what we did when we reported one was 999 mesh, and when we did with the 1661 mesh, you can see that all phonons are real. Energy in the energy cutoff we was reported 500, and in our case it was so. In some cases, people leave it negative or imaginary by considering that the phonon calculations for achieving the real or achieving the real phonon is very costly, or it will be time consuming, and therefore many times people leave the imaginary phonon that have both benefit. One, whether nobody is going to test, that is whether it will be the positive in any case or not, or whether it will be never positive or never real in any condition, right? So if it is never real, then it is not good. If we expect that with the higher calculation, if it is real, then it is acceptable and one should accept, right? So that is how basically we did it. Another case, because these are all reported when somewhere, and then we tried with SIG monolayer with buccal structure, and with energy cutoff 100 Rydberg imaginary phonon, 150 Estelle. When we go for the 200 Rydberg, it's real, right? That means basically what I want to say, this is the phonon calculation is a very sensitive to very sensitive to a structural and calculation parameter. That means that you have to have very good optimization, as well as you need to have the very high threshold value for these cases, right? So this is thermal conductivity. You can see that matters, right? When we calculated at 200 case, 200, that means in the stable case, the thermal conductivity is higher, and when it is unstable, the thermal conductivity is lower, right? So of course, having lower thermal conductivity is good, but the structure will be not stable, and therefore it is of no use, right? So it is another material, AuF3, and this is what we have published very recently. So you can see here that we have the experimental Raman spectra, and then we calculated Raman spectra by using the DFT, and then all other thing. It also shows the phase transition at 2 GPa, and at 0 GPa the phonon dispersion curves show all positive, all real phonon, and when it comes to another, that means at 2 GPa, it is imaginary phonon. And experimentally through X-ray diffraction, or maybe from other sources, even from the experimental Raman, it has been shown that there is a phase transition in AuF3 from P6122 phase to other phase, right? And that is what at 2 GPa it shows imaginary phonon, that means the phase transition, and that from the enthalpy also we can see for it goes to P61 phase, right? So enthalpy also tells us that there is a phase transition around 2.1 GPa when, and phonon dispersion also tells. So point is what? By calculating the phonon dispersion curve, we can know about the um, phase transition, a structural phase transition, and applying pressure, I mean, was that extreme condition, right? So we have applied to several cases, right? These are the people who worked on different areas. I have not been able to cover, but in different areas they basically work. Some of the results are in collaboration with people. So thank you very much. You all take care. Like, if you have any question, you can ask me. If no, then you can also, maybe you can send me through mail to me, or
Hey,
right.
yeah, thank you very much, Professor Jha, for your very interesting and comprehensive presentation. Yeah. So at this point, I think, yeah, we can move forward to the question and answer section. So yeah, if there is anyone who has a question, then this is a good time to ask it. So just please remember to unmute yourself if you want to speak first. Yeah, I can see that Tanvir Hussein has a question. So Tanvir, please go ahead and unmute yourself if you want to ask it.
Yeah, thank you, Gabriel. And thank you, Professor Jha. It's an excellent presentation. I'm sorry I missed the first part, but I really enjoyed this thermoelectric part. So, I mean, I'm not, very much familiar with this area, but you said like it's a thermoelectric phenomena is thus you change the temperature in a material and then you mobile the electrons.
Actually, the two end, one end you have to have high temperature, at another end you have to have low temperature. Right?
Low temperature, and the electrons would
temperature
move.
gradient is basically the result for temperature gradient basically produces the current.
Yeah, yeah. So in that case, the material is primarily like a need to be a good conductor of electricity. Is it true?
Yes, yes, yes.
Yeah, but in case of BN, I think it's a large band gap insulator. So
yeah, that is the question. But what I told that time, that we have one material that is simple BN, that is hexagonal or the cubic, and another boron nitride I was mentioning, that is the Haeckelite boron nitride. And in the case of Haeckelite boron nitride, the band gap is around 1 electron volt or so.
Mm-hmm. Okay. Thank you very much. And another quick, if I may ask, so this Haeckelite boron nitride exists experimentally, or it's theoretically?
Yes. Haeckelite gallium nitride, Haeckelite boron nitride has not been reported so far, but Haeckelite gallium nitride, Haeckelite zinc oxide, and all those things are available. Experimentally, people have grown it.
Okay. Thank you very much. Thank you.
All right, thank you very much, Tanvir, for your questions. Is there anyone else who would like to ask questions to Professor Jha? This is a good time to do it. Please remember to unmute yourself if you want to speak first.
Or they can put it in the chat.
Oh yeah.
Or you can send me later on the mail. I will.
Sure. Yeah. Yeah. Feel free also to write down your question on the chat if you prefer. I realize there's not many people who attended today, but that's probably because it's a Saturday. That's more of an organization issue. But as I said in the beginning, this presentation will be uploaded on YouTube, and I will also include the email of Professor Jha in the video description, so more people will be able to contact you in the future in case you have questions. But at this point, it looks like there are no more questions, and that we have also, essentially exhausted all questions. So I propose, in this case, to put an end to this webinar. Thank you very much again, Professor Jha, for your very interesting presentation. It was very, very comprehensive and covered a large number of topics. and I'm sure it will be of great interest to many people in the community to re-watch your presentations later on YouTube. So thank you very much, everyone, for attending today. And of course, please stay tuned for the next webinar. I will send you more information in the coming days about the next upcoming webinar, but it should be sometimes around the beginning of August. And hopefully we'll be able to continue attracting even more people and even more speakers in the future. So thank you very much, everyone, for attending today, and have a good day or good night, depending on where you live in the world. So thank you very much. Thank you.